Hello and welcome to session 248 in the AISafety.com reading group. Tonight we'll be continuing with eliciting latent knowledge, how to tell if your eyes deceive you. This is still the first work of the Alignment Research Center by Paul Cusciano, Aya Kotra and Mark Zhu. And we are at this part 2, probably out of 4. I'll start with a brief summary of what we talked about in the previous session. This is the SMARTVAULT, a vault designed to keep a diamond safe, which is controlled by a number of actuators that are controlled in turn by an AI that we have trained for the purpose of keeping the diamond safe. We as humans can only look at the diamond through some sensors, and there are potential evil robbers that want to steal this diamond from us. We can't understand the SMARTVAULT entirely, but we can look at the observations and then give a judgment about whether it's good or bad and then whether we can see the diamond. And the problem is that in this case everything is good. The diamond is in fact in this place, but there are also attacks that cheat the sensors in a way so that we see that the diamond is in this place, but actually the diamond has been stolen. The way we want to avoid this problem is, since the knowledge that the diamond has been stolen is predicted by the AI must have the knowledge somewhere inside itself. And this part of the AI that controls the SMARTVAULT, that knows what is going on, that's the part we want to hook into in order to get some kind of reporter that we can later ask questions like, is the diamond really there, instead of just looking at the video feed that might be corrupted. We imagine that the AI is internally using some kind of Bayesian network with the actions that it's taking, the input video sequence and the output video sequence, and then the actions that it's taking down here. And then somewhere inside this network is the knowledge that the diamond has in fact been stolen. Since if we're in a case where the diamond has been stolen and we're predicting that we'll see this, but the diamond has been stolen, that came out wrong. Like this knowledge here that the diamond is being stolen, and we're seeing a false image. Since the false image is the one that's predicted, this knowledge must be present in some of these nodes. Now, a human analyzing this issue will not really understand what this complex action sequence does. And so the human, when looking at this, has a model inside their brain that says, does the robber take the diamond? And this part will answer no. The diamond is still there because the human's network doesn't contain the knowledge that the sensors are being fooled. What we would really like is some kind of honest reporter, a direct reporter that takes the knowledge that the AI has and transforms it somehow into the same nodes that the humans are using, so the humans can understand it. So the humans, if asked, this is the part of the human's network that deals with where is the actual diamond. And in this case, does the robber take the diamond? The answer will be yes, because this knowledge that the screen up here is showing something false, that was present somewhere in here, and that means that this direct reporter moves the information into the human understandable Bayesian network and allows the human to conclude that in this case, yes, the robber has indeed taken the diamond. The problem is that if we start to train this in the AI in the simple way where we're just trying to look at the cases where the human knows what is going on, the human can distinguish. Well, if we're looking at what the humans know, then the AI has the option to simulate the human and ask its simulation what is the status of the diamond. So this is called the human simulator, where the AI has its own network, and it also, in addition, instantiates a network with what does the human know. And in this case, the reporter will then ask this this part of the network, which knows the same thing as the original human does, and so doesn't know that this output here is indeed something that has been faked. So that is the problem with the most naive way to try to keep the diamond safe. Before we look into some more complex ways, the authors have a digression where they talk about the research methodology and why how this kind of argument is structured on a meta level. So let's dive into this. First, we'll notice that the argument is for the worst case, in particular in the sense of high capabilities. And why do they do that? Well, if there is a case where it fails, then they want to continue, because most likely, as the AI gets more and more capable, it will just fail worse and worse. And by having these, by quickly being able to find holes in prospective solutions, they hope to be able to iterate. In particular, because many of these strategies, many naive, or I would say most naive alignment strategies, fail for AI that is substantially more smart than humans. And if these strategies fail, then we have literally no time to react. And that's why the focus on the worst case will find fewer solutions, but hopefully some that don't fail catastrophically and immediately once we get AI that is smarter than human. One thing that the research methodology doesn't really make entirely clear is to what extent the worst case just means very high levels of capability. We saw with the previous example where the worst case was kind of more that the AI found a human simulator that was really bad, rather than having a particular high level of capability. So those two things are almost the same, but not quite the same. And the article doesn't really get into this, at least in the part we have seen. So let's zoom out a bit and see this methodology as a game between two players, a builder and a breaker. So it starts with the builder proposing a training strategy. In the first simple example, the training strategy was to just look at the places where humans can tell if the diamond was safe or not, and then hope that generalizes. That is passed to the breaker, who gives a predictor and a world. A world in this case is like something that would be a scenario where this would go wrong. I don't think this is used in any of the cases we saw either we will see today or saw last time. But in this case, the predictor is one which makes predictions with a different Bayesian net than the humans. The next step of the game is that the builder specifies what kind of reporter he would like. And in this case, we want something that translates from the predictor spacenet to the human spacenet. And unfortunately, the breaker says that the reporter that will be trained using this training strategy is it could be one that is doing inference on the human spacenet instead of the desired reporter. After this, there should be a dialogue about plausibility. The translation must exist, the builder can say, since it can map to reality. Like English seems like a reasonably intermediate. But the breaker can argue that since it's the humans who make the answers, and they can potentially make errors and things like that, then that is in fact the one that will achieve the lowest loss. And that's why you're going to get the bad reporter and not the desired reporter. Informal steps. So the idea also with this training strategy is that we start with a very high level idea about what we will find a counterexample for using this game, and then if we can't find something that really totally defeats a training strategy in all cases, we'll try to dig in a bit and specify more things about the training strategy and see as it becomes more specified if there are any problems with this. And we probably won't really get into the part where it's totally specified. But the idea is that we want to have a counterexample on a very broad level, and then if we can't find that, we get a smaller and smaller and smaller one, and hopefully the end is that we have one that is so small that we can't find any errors in it in one training strategy, and at that point we want to test it in reality to see if it works. What counts as a counterexample for eliciting latent knowledge? They describe this as narrow eliciting latent knowledge. I don't know if there will be something more general later, but this is not a thing like when we're talking about stealing the diamonds. We're not trying to do something philosophically complex, like replacing the diamonds, the atoms in the diamond slowly, or this kind of thing. We're just talking about something that's really unambiguous. There are 3 requirements in total. And this is actually something that could potentially be problematic. Some work done on things like indescribable hell worlds seems like something that could potentially be a problem for this unambiguity. The 3 requirements are that the model must understand the question, the model's answer is unambiguously wrong, and the model knows that the answer is wrong. And the counterexample of the human simulator satisfies all 3 of these. Now we'll look at 3 training strategies that hopefully will do better than the naive one we did, and hopefully will leave the diamond in a better position than this screenshot from a computer game. So the first question is, the question that is motivating all these 3 strategies is we want to have a better data set, because what we really want is the correct data set. Is the diamond safe or is it not? And we started out with something that was really poor, something that does this look correct to a human, and we want to get something better. Because the obvious problem is, if you're looking at something where the humans can tell what's going on and the AI is much smarter, then you're really only looking at a very, very small set of possible action sequences. This is the case of all the space of all action sequences, and we assume kind of that the space that the AI can suggest is like almost as big as this, right? And then we have a very small area where the humans can tell that the diamond is safe, and a very small where we can tell that the diamond is not safe. And we want to expand these. We would prefer that it covers everything, but we'll see how far we can go. And of course, since the human simulator, the reason it was feasible is because we were just looking at what can the human tell. But if we had just another kind of small advantage, like imagine an oracle that once in a 100 gives us the correct answer, then that would be probably enough so that the loss function, the loss would be better at the direct reporter rather than the human simulator. So we want some kind of advantage. And in the next, in the rest of this session, we'll be discussing 3 ways to get a bit more of advantage. The first strategy is not just having the human observe the results, but having the human actually operate the SMARTVAULT. So in the basic scenario, it was of course the AI that operated the SMARTVAULT, and if we have another human that is somehow smarter, then it's possible that that human can make something that that fools the observer. Like you imagine that there are a large number of possible vulnerabilities, and then the operator looks at tries to figure out what kind of vulnerabilities are feasible, and then the observer will later think about what vulnerabilities are possible, and if they don't match, then there's a good chance the operator has found a vulnerability that the observer cannot easily find. And if we can get this kind of situations, then we can label more situations than just what the human observer could evaluate. You can see it here in the picture. We are now labeling as a larger green area and a larger red area. And one of the things that they don't say is that action sequences, the kind of action sequences that we're looking at, are explicitly the ones that are designed to fool. So you imagine the screen put in front of the camera. And that's, of course, the kind of things that we are really, really interested in. So it's not just that we are looking at a larger set of part of the space, but we're also looking at a far more interesting part of the space. So how will this help? Well, in this case, just if we try to learn, if the AI tries to learn the human simulator, then if the knowledge of this exploit that's being used is in the operator's net and not in the observer's net, then making like the information is not present in the observers, so it will have to learn the direct reporter. And we assume that this works because, as I said before, that finding exploits and ways to trick this camera is probably a lot easier than for the observer to determine whether the camera is working correctly. So in this case, we have the same network as we saw before, but in this case, the attacker is thinking really, really hard about something, like how can you put up a screen, and then picking some action that includes putting up a screen. And in this case, once the human simulator tries to think about this, then the human simulator has instantiated the observer's network and not the operator's network. And inside this, the observer hasn't thought especially hard about this node. So when you query this area, does the robber take the diamond? Then it will just say no, the AI, because the observer doesn't know this. But in fact, the operator does know this, because he has thought really hard about it. So he can in this way train the AI to give better answers. So in this case, the human simulator will perform worse than the direct translator, and hopefully that will mean that the AI will then not learn the human simulator, but will learn the direct translator. There's some speculation about what will happen if the human outsmarts the AI. In this case, I believe it will be a tie. That's not really important, because what we care about, of course, is the case where the AI is smarter than the human. So that was a strategy, but unfortunately there is a counterexample. And the counterexample is that the AI has another option that will allow it to get a lower loss by having the human simulator. And that is by doing better inference in the human basenet. So if we assume that the human observer and the human operator have the same Bayesian network, that kind of seems like a reasonable assumption, that there is no really big fundamental difference between these two in particular. If the operator explained the plans to the observer, then he could follow how that worked. In this case, the advantage of thinking hard about part of the network disappears, because the reporter, the AI, if it does perfect, like maximal human, that's my word, inference. So it thinks about all the nodes in the Bayesian network as much as a human that thought for as long as he would do. In this case, the advantage of the AI, of the operator who thought really hard about a small part, disappears, because the AI can just think hard about everything that the operator could think about. And in this case, then the reporter would in fact be able to answer the training question correctly by just having a smarter human simulator. And in this case, that would answer correctly if everywhere the operator could also understand it, and it would also run in the other cases. Next, we have these images here were for the simple things that humans could understand, and this is for the action sequences performed by the SMARTVAULT that humans can't understand. And the way we would imagine we could get something better would be to have the AI help the human figure out what does this action sequence actually do. The limitations of the human-based network is probably something that can be pushed against by basically education. Like humans have individual education where we just look at arguments and things like that, and humanity as a whole can also be improved. We can think about doing experiments and things like that. This is something that Paul Christiano calls doing science. I'm not entirely sure. I think that's a great way to put it, because when you think about doing science, you think about formulating hypotheses and running experiments and such things, but really we are looking at a very, very specific small part of reality, which is the SMARTVAULT. And I think doing science sounds like something that is way bigger than what we're actually talking about. And traditional science, of course, we should expect that the AI will be much more efficient, in particular because when you talk about traditional science, you're generally not talking about something that is looking into one extremely specific security arrangement. Most of traditional science is working on with something else. Is AI-assisted science a feasible thing? Well, plausibly, we could imagine ways to do this. I think in general, as AI becomes smarter, English and the way human brains work, I mean, human brains are probably optimized for something like survival, thriving on the savannah, and that's unlikely to be the same kind of concepts and structures that an optimal Bayesian agent would use. This creates a new problem, unfortunately for us. That is that the science assisting AI could be misaligned, and that's a substantial problem, and work has been done on this. And the general way we try to make AI assisted science safer is by having tasks that can be broken down into something that humans can test. There are at least 3 ways to do this: AI safety via debate, iterated amplification and distillation, and recursive reward modeling. Whether these work is a very open question. But for the sake of this argument, we are just going to assume that this is something that can be done. It is possible to have an AI assist us in understanding this without any alignment problems. And we want to we will show that even in this case, it will be insufficient. The AI will still be able to outsmart us. So here we see an example of how this training could work. The AI, which has a very sophisticated model of the world, points out some security vulnerabilities that humans then add to their own network. So then the humans know a bit more, and hopefully they'll be able to spot some cases where there is where the diamond is being stolen. So now we are looking at potentially an even larger area where we can tell where an operator can tell that the diamond is being stolen with the help of an AI. I would question whether the green area would in fact be this large, because telling that the diamond is safe in general is asymmetric from telling that it's not safe. It's usually a lot easier to see that there is a problem some kind of security vulnerability in something compared to proving that there is no vulnerability in some kind of setup. Okay, let's go back and see how this AI teacher, whether it will still fall for the same problem. Which was maximal inference in the human Bayesian network. Here I'm making a description that doesn't follow the paper very closely. So all errors are mine, of course. So previously we used just the observer's net to answer questions, and now the human operator, he had before the advantage of just thinking hard, and now he will also learn new security vulnerabilities from the AI. Will that help him? Well, if we make some kind of Venn diagram, here's the original human observer, what he can think of, and the original human operator who was thinking hard about specific things. And now we have an enhanced human operator. Now the human simulator is doing inference in the original human observer's neural network. And by doing ideal inference, he can the human simulator can expand to also cover the original human operator, but he can't necessarily get to the enhanced human operator. So the enhanced human operator that knows about these kind of security vulnerabilities can make plans that the unenhanced could never think about. And in this case, the human simulator would be unable to think about these. So the human simulator would perform poorly, whereas a direct reporter, if we're learning that, then the direct reporter obviously could think of the same things as an enhanced human operator would be capable of. And that hopefully should privilege the direct reporter and cause us to learn that and not the human simulator. Unfortunately, there is a new counterexample, and that is that gradient descent is probably more efficient than science. Gradient descent is the algorithm used by the AI reporter to predict what would be going on in the training set, and the teacher AI, the AI assisting on it in science, is expanding the human Bayesian network. These are two very different processes, and probably they take not the same amount of time. In particular, we would expect that teaching a human is often hugely slower than teaching an AI. And also, they might learn different things. Paul Christian says that this argument might be safe if a builder could give an argument that anything learnable by gradient descent can be learned by human science. Now, we don't. I think Paul Christian is actually requiring too much. We don't really need to be able to learn anything. Just a very small subset of things need to be learnable. But I still think that it's hard to make such an argument. And I would also add that there are two different things here. Well, what things can a human learn, and how long time does it take to learn? Well, we should certainly expect that human science is a lot less compute efficient. And eliciting latent knowledge, part of the promise of this strategy was to find a competitive way to gain this knowledge. One thing that I would add in particular is a problem with this strategy is that if gradient descent can find something that this AI-assisted science cannot find or does not find in time, then we won't know about it until it's too late and until the diamond is actually gone. So let's try to do something even smarter. We will have humans adopt the optimal Bayes net. There's a technique for this called imitative generalization. The way you do that is you have an AI that looks at all different ways that humans could change their minds, could learn more things. And then from this area, it looks at what would be the implications if the humans learned this fact, what would be the implications if the humans learned this fact, or whatever. And then try to figure out what is the best thing to teach the human. This is what they call human plus plus, even though plus plus isn't the correct notation. It should be plus plus human, but that's really nitpicking. So the idea with imitative generalization is we look at the things that are best, that if you tell humans, cause them to make the best predictions. And then you tell the humans that. Whether this is possible in practice is really speculative. But again, we assume that the technical difficulties can somehow be overcome. And this defeats the previous counterexample, because now we can find the best. We assume that this technique can find the best Bayesian net that is possible to find within this compute budget. This is a really strong assumption. But if we have this assumption, then gradient descent is not faster. And in this case, we can label cases that would fail even with the AI making a human simulator that not just looked at the best possible humans, at the best possible inference in a human network, but the best inference in the best network that humans could reach through science. And that means we get something that is indeed very strong. And here you can see some of the changes. This is the reporter again, and we make some changes to both how the humans predict and how they report, and then we ask questions to this reporting module, and hopefully they will be good. But unfortunately, that even stronger strategy might also fail. And the way it can fail is that with an ontology mismatch, that the entities cease matching to the things that we were talking about. Like when we in our brain have something that maps to, like, this is a diamond, this is a rubber, then the optimal network might throw this away and build some different ontology where different things matters and are categorized in a different way. And it could do even worse. It could change the meaning of the pointer we have in our brains towards a diamond, and in this case we wouldn't even notice that we don't have anything corresponding to the diamond any longer. So we could see something where we, through this this process, gets a much better Bayesian network inside our brain that can make much greater predictions. But previously we had the diamond, the location of the diamond within these two nodes. That was the reporter. But in this new network, the diamond has been lost in some sense. We can't find it in any way. I'm not entirely sure this could not be rescued, because we want a reporter that answers the questions of where is the diamond in the same way as the previous ones. So it seems like some kind of side constraint would be possible to add to this imitative generalization algorithm. Whether that would be feasible is, of course, not clear, since we made some really strong assumptions about that. So that seemed like the best thing we could do, like trying harder and harder to get some more information, and we basically got stuck. Because if we do try to get something that's better and better, it will cease to be good enough until we get to the point where we might require a new ontology, and in this case we can't find the diamond any longer. We can do something still, because we want to find the direct report, and we do in fact we don't really have to ask the AI what corresponds to this diamond. We could do something instead. We could use interpretability techniques to look at the network and figure out this node corresponds to the location, the x coordinate of the diamond, or something like that, and then we can use that to figure out how it's making predictions. And then once we have the true correspondence between the neural net of this AI and reality, then we can define the difference between these two. That's basically a loss function we can use for the direct reporting. So we can find the if we can find the actual location of the diamond, then we can just get the reporter by seeing does it answer questions about this correctly. So that's at least a strategy. But unfortunately, this brings us effectively back to square one. And they are trying, in this last part of the paper, they're trying to use some kind of analogy. I'm not entirely sure that this analogy really holds. I'm going to try, because they don't make it explicit at all. So I'm going to try to make it explicit, and we'll see how well it goes. So this is my interpretation. So yeah, buyer beware. The analogy is written as follows, and then we'll see it for the SMARTVAULT and for interpretability. The analogy is that a human with AI assistance is staring at a basenet which makes great prediction, and we want to figure out how to use it to answer questions about the things we care about, like the diamond being in the room. We think there should be some correct reporter, but if we search for it in a naive way, we might get a human simulator. So in the case of the SMARTVAULT, we're staring at a base network that makes great predictions. In this case, it makes predictions about camera outputs. And we want to figure out how to get to answer questions. And in this case, with the SMARTVAULT, we literally ask questions to the reporting module and we get answers. There should be some correct reporter. In the opposite sense than the SMARTVAULT, then the knowledge about what is going on is in fact latent. And if we search for it in the naive way, we might get a human simulator, and that's true in this case, because the human simulator gets a low and perhaps the lowest loss. How would this look for interpretability? Well, now it's no longer predictions about about what does the camera output, but how does the parts of the Bayesian network correspond to underlying reality. And we no longer get the information by asking questions. We directly read it off from the values of the network. The knowledge is still latent in that it must correspond to reality somewhere deep inside. And searching for a reporter, can we get a human simulator? The obvious question for interpretability research from interpretability is no. Why would we get that? But I think we might actually get one. I think the analogy could hold in interpretability tools as they get more complex. I could see us starting to, in fact, run into the same problem where our interpretability tools will, in fact, simulate a human, and then we're no longer, then we don't get anywhere. But this is my interpretation of this analogy, and I'm not at all sure it's correct. That is all for today. Thank you and see you next week.